I'd like to start this video just talking in general about right triangles. Okay, when we have a right triangle, there is always a relationship between the lengths of the sides in every right triangle. And the first way that we learn to describe this relationship is the Pythagorean theorem. Okay, the Pythagorean theorem tells us a squared plus b squared is equal to c squared. And what that describes is the relationship of the length of the sides, given that c is the side across from the right angle, and that the other two legs of the triangle can be called A and B, and these are interchangeable. It doesn't matter which is A or which is B. Now, when we label the legs and the hypotenuse this way, if we take the length of A and square it and add it to the length of B squared, it is equal to the length of C squared. This is extremely helpful because it allows us to solve for missing measurements. But the one drawback here is that we have three variables. And so in order to find a missing variable, we have to have two of the three. Now, we have that in a lot of cases, and this is a very helpful theorem. However, we have other ways to describe this same relationship that may be possibly more helpful. Okay, so the next one that we talk about are called special right triangles. There are two of these. So again, this doesn't work in all situations. Pythagorean theorem works on every right triangle. But again, we have to have two of the three. The two special right triangles we talk about have to do with the angle measurements. Okay, this first one, of course, it has to be a right triangle, but if the other two angle measurements are 45 degrees, the relationship that exists between the lengths of the sides can be described using only one variable, which allows us to solve for missing sides when we only have one of the three sides. So, if this side across from 45 we call x, the side across from the other 45 we call x, which shows that the legs in 45, 45, 90 triangles are always the same, and then the length of the hypotenuse is x times the square root of 2. Okay, so let's see exactly what that means. That means that if I have any side, so I'm going to say I know that one of the legs is 5 inches. So if this leg is 5 inches, well, the other leg is also 5 inches. And then that says that the length of the hypotenuse is 5 times the square root of 2. 5 times the square root of 2, it's a number. It's, 7 point something. But that's an approximate answer, and this is an exact answer. Now, of course, we can use Pythagorean theorem to see this. A squared plus b squared is equal to c squared. So say all we knew is that this side was 5. Well, again, we also know that this is an isosceles triangle, so the other side is 5. So we can say 5 squared plus 5 squared is equal to c squared. And we get 25 plus 25 is equal to c squared. We get 50 is equal to c squared. So c is equal to the square root of 50, which we can rewrite as 25 times 2. So c is equal to the square root of 25 times the square root of 2. And so the square root of 25 is 5, square root of 2. Okay, you could go through and solve each problem this way, but what we're saying is that this relationship always exists. So if I go over here and I change this and I say, okay, let's see, x is, let me fix this, sorry. Say x is 8. Well, I don't have to solve for the other side because I know if that one's 8, this one's 8, and this one is 8 times the square root of 2. Okay? If you know that, let's say, x is 13, well, then I know that this side is 13 times the square root of 2. and this side is also 13. So it helps us solve problems without having to do the actual arithmetic because we know this pattern always exists. Okay, let's look at another one. So again, 45, 45, 90. When you get these problems, it's very helpful to label this way: x, x, x to the square root of 2. What happens now if you're given that, let's say, the hypotenuse is 10 to the square root of 2? Well, what are the lengths of the legs? Well, they are 10 because this is 10, 10, 10 to the square root of 2. So if they're nice enough to give us the hypotenuse as anything 7.5 times the square root of 2. Well, the other side is 7.5. So those should be easy to look at and see. Now, let's see what happens if, let's look at, let's look and let's say that, again, it's very helpful to just write x, x, x to the square root of 2. Now you get a problem where they say that the hypotenuse is 10. Not 10 to the square root of 2, but just 10. Okay, there's also a pattern here, but let's solve for it and see what we get. Okay, so Pythagorean theorem is a squared plus b squared is equal to c squared. But in this case here, a and b are both the same, they're x. So I'm going to call this x squared plus x squared is equal to 10 squared. Okay? So you can say 2x squared, is equal to 100. Divide both sides by 2. I get x squared is equal to 50. So x is equal to the square root of 50, which is, let me put over here, the square root of 25 times 2, or x is equal to the square root of 25 times the square root of 2, or x is equal to 5 times the square root of 2. Okay, so if the hypotenuse x times the square root of 2 is 10, the other side, x, is 5 times the square root of 2. And I'm going to tell you that that relationship is always, if this is 20, this is going to be 10 times the square root of 2. So anytime you have an integer number over here, 10, 20, 8. If this is 8, the other side is half of 8, 4 times the square root of 2. So it is going to be half of the integer times the square root of 2. Let me show you one other way that we could solve for this. Let me just put the same picture back up. 45, 45, 90, x, x, x to the square root of 2. And let's say that this is, we said it was 10. Another easier way maybe to solve for it, but you got to make sure you remember some of the radical rules, is that we were just given an equation, x is equal to the square root of 10. So let me write that, and let's just solve that equation for x. Well, if I want to get x by itself, I have to divide both sides by the square root of 2. And x is equal to 10 divided by the square root of 2. That is a true statement. However, there's a radical in the denominator. If you are allowed to give a decimal answer, you could put that in your calculator, but most times you're going to be asked for an exact answer. So we have to rationalize the denominator by multiplying by the square root of 2 over the square root of 2. In the numerator, we get 10 times the square root of 2. In the bottom, we get 2, and we simplify. 10 divided by 2 is 5, and you can see that the answer is 5 times the square root of 2. Okay, so let's look at one problem then that the pattern itself won't be as obvious, but how we would solve for it. So 45, 45, 90. So we know the pattern is x and x and x times the square root of 2. So what happens if this time they tell us that the hypotenuse is 6 times the square root of 3? Okay, now that's not one that I actually can really, off the top of my head, tell you what the other side is right now. So, but I can solve for it. I know that x times the square root of 2 is equal to 6 times the square root of 3. I need to divide each side by the square root of 2, and that's what I get. So again, just follow the rules of radicals now. Multiply by the square root of 2 over the square root of 2, and I get 6 times the square root of 6 over 2, and I can simplify. 6 divided by 2 is 3, and you get 3 times the square root of 6. So x is 3 times the square root of 6, and so that would be the length of both of the legs. So we can just set up and solve the equation that's given there. Let's look at one more, and that would be 45, 45, 90, x to the square root of 2. So what if you're told that x is equal to 5 times the square root of 2? Okay, just change colors here. That means that this side is 5 times the square root of 2, this side is 5 times the square root of 2, and this side is x, 5 times the square root of 2, times the square root of 2. Square root of 2 times the square root of 2 is 2, times 5 is 10. Now let's briefly look at the 30, 60, 90 triangle. The pattern that exists in the 30, 60, 90 can be described with x across from 30, 2x across from 90, and x times the square root of 3 across from 60. And so again, everything is kind of the same. You have to be given one of these sides, but let's just say that, oh, I'm sorry, I didn't mean to do that. Let me draw it just again. 30, 60, 90, x, 2x, x to the square root of 3. So if you're told that this side is 10, you've got 2x is equal to 10, so 1x would be 5, and this side would be 5 to the square root of 3. The rest of the rules are the same. You're going to solve. One thing to keep in mind with the 30, 60, 90, though, is let me draw it this way. Okay, 30, 60, 90. When you're trying to decide where your x, 2x, and x to the square root of 3, x isn't necessarily on the bottom. It's across from 30. So in this case, x is here. 2x is here. X to the square root of 3 is here. One last thing I'll say here, I just have a couple minutes left before I run out of time. A lot of times when you see the 45, 45, 90 triangles, they'll talk about them in terms of a square. So if you have a square, all of the angle measurements are 90, okay? But they'll say we draw a diagonal of a square. So if I could draw this a little bit better, anytime you draw a diagonal in a square, you have created two 45, 45, 90 triangles. So just keep that in mind, and that diagonal is going to be the x times the square root of 2, and this is x, and this is x. Okay, so that's how you would see that in a square, and the 30, 60, 90 is found inside of an equilateral triangle. So if this is an equilateral triangle, all my angle measurements are 60. Well, if you draw the height in this triangle here, the height bisects that angle at the top and makes two 30-degree angles, and it creates a 90-degree angle here. And then if the lengths of the sides were all the same, say they were all 10, when you draw the height, it bisects the base and here. And that's how we create our 30, 60, 90, where we have x, 2x, and x to the square root of 3. Okay, I hope this video is very helpful in giving you an overall picture of special right triangles.